Section 12.4, we are getting into vector equations of lines. Just like the normal equation of a line that you guys are used to, just think of like a y equals mx plus b equation of a line. That's exactly what this is. It's just in the form of a vector. And so if you look at what we're going to be getting into here in a second, the equation of vector r, if I'm going to write it as the equation of a line, like y equals mx plus b, think of this as y equals mx plus b. So x is like our variable that we have right here. The direction vector that we have right here is kind of like the slope. It's the direction of the line or the slope of the line. And then the position vector that you have right here is just a point on the line. Typically it's the initial point on the line. But it's the same idea as far as just doing like a y equals mx plus b concept with these. And so you can see a couple ideas right here. So normally if we were going to take a look at vector AB for a minute, and so we know that we would do the terminal minus initial, so B minus A. And so if I did that for the numbers that you see over there on the right, this is the direction vector that we would get for AB. And so in terms of the equation of the line that we're doing, the direction vector is like the slope in that sense. And so if you, that's what this guy is going to be right here. It's like the slope of the line or the direction vector. Think of it in terms of rise over run. We rise 1 and run 4. So if I from here, if I go up 1 over 4, right, I get the direction of AB from A to B. If I think of that in terms of rise over run, right? This is the horizontal component and this is the vertical component. So rise over run. So pretty simple if you think of it in that terms. The position vector that you see here, if you think of this in terms of y equals mx plus b as like the b, or this is normally like what we would call the y-intercept, but not always going to be the case for a vector, but it is just represents a point, or what we call the position vector. So for the one that we were looking at up above, right, this was the initial point for this vector r that we did in this problem right here. So we had the initial point plus the direction vector that we did on step number 1, and t is t. That's just a variable. It's like if you're doing y equals mx plus b, you'd always have an x sitting right there, and so t can represent any scalar that we want to use it for within that setup. But this is the main idea that we're looking at right there. So again, it's the initial point plus our scalar or constant times the direction vector. Keep one thing in mind as far as vectors are concerned. The difference between something like this and something like this, the direction vector is always going to be used in terms of velocity. Whereas if we were going to do something like the speed, then we take the magnitude of the direction vector to do something like speed. All right, so looking at down here at a couple examples. So if our line is going to be passing through this initial point of 9, negative 7, so that's going to be this guy right here. That is the initial position vector for 9, negative 7. And then if it's parallel to this one, that just means it's running the same direction. So if you think of that in terms of slope, anytime you had parallel lines, they had the same slope because they were going the same direction. So I'm going to use the same horizontal component and the same vertical component that this one had, and we're going to use that for our direction vector as well. So we have the initial point right here of 9, negative 7. So remember, in terms of ordered pairs, this is x and y. We always put the horizontal on top and the vertical on bottom. So x then y. And then right here we have the direction vector. So again, parallel to this one, so we're just using the same components that vector v had since they're parallel, and that's going in there for the direction vector. You can write it in terms of this in column form. You can also write it in terms of I and j like this one has. Neither one is more right than the other. You can do it either way. Typically, I see most people go with this format. It seems to be the most comfortable for people. For number 2, if we said the line containing these 2 points, again, just consider this equation in terms of y equals mx plus b. We need a point on the line. Typically, we do look at this as the initial point. However, it can just represent any point on the line. And so in terms of this, I'm going to be able to use this one or this one for my position vector. And so that's why you're going to see, if you look down here, there's two different ways we could write this answer. So for the position vector that you see here, you could either have used this point or you could have used this point. Either one of those could have acted as our position vector. But for this part right here, just like getting a slope, this is my horizontal component, so this would be the difference in the x's. So for this one, I'm doing -2 minus -6, and that's the horizontal component. This is the vertical component, so that would be the difference in the y values. So in this case, 4 minus 7. And there we go. That's our direction vector. Again, if they ever refer to, say, length or speed, we know we would take the magnitude of the direction vector to get things like that. Looking down here for this. So again, for the slope of the line, we would typically see this as rise over run. And whenever we've done a slope fraction in the past, you've always done rise over run. You put the y on top and the x on bottom. So keep in mind that that's different for a direction vector. We put the horizontal on top and the vertical on bottom. So just keep that in mind. This would be if you were asked about the slope of this line, we would see it as -3 over 4. Perpendicular, right? Just like where the parallel lines have the same slope, well, perpendicular lines would have opposite reciprocal slopes, and so you're kind of seeing that laid out right here. One thing to keep in mind, you could put the negative, so if V is CD, then perpendicular to that could either be -d over C or d over -c. You could put the negative with either value, it doesn't matter. Either way, you get the same direction vector. So if we had looking for the equation of a line passing through 7, 3, scroll down a bit, and perpendicular to this vector right here. So again, we know the position vector of 7, 3. So that's our p-value that we're going to have in right there. As far as being perpendicular to this, you're just going to switch the numbers, and you got to make one of them negative, and it doesn't matter which one. So if this one had a horizontal component of 2 and a vertical of 9, just switch those. We're going to put the 9 on top and the 2 on bottom. So we're switching the order, and you can put the negative with either value. And so again, this is one way to write the answer for the equation of this vector. They put the negative for the 9 on this one, but you could have put it with the 2. So this could say 9i plus -2j. But this would still be the same as far as the position vector. Point of concurrency, or the point of intersection of two lines. So here we have the first vector, so that's the first equation of a line. Here's the second equation of a line. And if we're going to find the point where these two guys intersect, so we're looking for that point that they have in common, well, we're simply going to set the two equations equal to each other and solve. So one thing you're being introduced to within the work on this is something called a parametric equation. A parametric equation just does the equation with one component, either the horizontal or the vertical. So if you look at this one right here for a minute, the horizontal parametric equation of the first vector would be -3 plus 4t. That would be the horizontal parametric equation. The vertical parametric equation would use the vertical components, so 5 plus 3t. Same thing on this one. The horizontal parametric equation would be 2 plus 1s, and the vertical would be 17 minus 2s. So if I'm going to solve this as like a system of equations, we're going to set the horizontal components parametric equations equal to each other. And that's what you're seeing right here. This horizontal would equal this horizontal. That's 2 plus 1s. And then we set the verticals equal to each other. So 5 plus 3t would equal 17 minus 2s. And we just have a system of equations to solve right here. So we can use elimination or substitution, whichever one you feel comfortable with. Elimination was used right here in order to figure out that t is 2. You plug that back in and you figure out that s is 3. One thing you really have to keep in mind is that t and s are not your answers. A lot of people will stop here on a test and give me those two answers as the point of intersection, those are not points. Those are the numbers you need to get the points. And so here's a better look at what we have right here. We are solving for an ordered pair. And the video that I attached to this on the calendar does a good job of showing you where this comes from. So you might want to take a look at that video as well. So again, I'm looking at the top row here for the x values and the bottom row for the y values. So we can now replace t with our value of 2 and then just simplify from here to get the x coordinate. So I would do -3 plus 2 times 4 to get the x coordinate. I would do 5 plus 2 times 3 to get the y coordinate, and that's where these come from. You could have used a value for 3 for s and replace this with a 3, and you would get the same answers for 5 and 11. So if you did 2 plus 3 times 1, that would also give you 5. You could do 17 plus 3 times -2, and that would have also given you 11. So you get the same answers no matter which of those equations you choose to work with to get your ordered pairs. So last part right here, same concepts. These are just 3-dimensional instead of 2-dimensional, but there's really no difference here. The line containing these points, so I'm just going to use the first one as my position vector. You could have used either one as your position vector. Either one would be right, but that's going to go in as the position vector. And if I want the direction vector, you simply find the difference in the components. So this is the difference in the first components, and that goes first. I have the difference of the middle components, and that goes in the middle, and then the difference between the third components, and that goes on bottom. And so this is how we came up with a direction vector. And so here's the format, same format that we were using up above: position vector, direction vector, and we got that right there. A couple different ways that you could have written this, and it still would have been considered right. However, this tends to be the most commonly used. Last one right here, again, this is another point of intersection between two lines. I would encourage you to give this one a try, real similar to what we did up above, but we're going to use parametric equations to solve it. And so in looking at these guys, here they are kind of laid out, one with the t's, one with the s's. You would solve this one the same way that we did the one up above. So I would encourage you to give this one a try and see if you get it right. This is what you should come out with if you do it right. So give that one a try and see if that process works for you. So for this last one, we're looking to see if these guys are concurrent, meaning do they intersect? Do they have a common point? Are they parallel, or are neither of those true? Let me start with the parallel. This is the same idea that we did in an earlier lesson this chapter. If they're parallel, then this would be a scalar multiple of this. And notice I'm using the direction vectors for this, not the position vectors. Right? I'm looking at the direction to determine if they're parallel. So if I look, does 2 divided by 3 equal 5 divided by 1 equal 2 divided by -3? Right? Those are not all equal. Therefore, this is not parallel. So it's not, because they're not scalar multiples of each other. As far as are they concurrent or do they intersect, doing what we did up above, solving for t and s. And so these are the parametric equations that you would write for this. And you just need 2 of these to solve a system of equations. You don't need all 3. Just pick 2 easy ones and solve for s and t. Once you solve those for s and t, you came out with s equaling 1 and t equaling 4. Plug those back in and see if we get common points. So if I replace this t, or let me go to these. If I replace any of those t's with a 4 and replace any of those s's with a 1, does this number equal this number? Right? I'm checking to see if they are equal. Does this one equal this one? And does the last one equal the last one? If they do, then yes, they're concurrent. They have a common point of intersection. But if not, if they're not equal, like on this one, they're not, and you can test those numbers by plugging them in, then we'd simply say that they are not concurrent.